Assalamualaikum to Dr. Razi, uh, the special my lecturer in mathematics engineering. Today we can as we have explained about the chapter 1 of mathematics engineering 3 in module UTHM semester 1. Alright. Uh, we Now I have explained about the partial derivative. In mathematics, a partial derivative of a function of several variables is its derivative with respect to one of those variables, with the others higher constants, which are opposed to the total derivative in which all variables are allowed to vary. Partial derivatives are used in vector calculus and differential geometry. Partial derivative have three features, which each number one of features. First order partial derivative, second order partial derivative, and the mixed derivative for the last one. The application of derivative also have features which is can divide to six, which is a tangent plane, slope of surface, rate of change, small increment, and approximations, analysis of corrosion, analysis of error, and local extreme value. The features of the application normally can use for solve the problem about the partial derivative in math engineering 3. Now we go to the slide and look at the question. We can read the problem in the real world application in the features rate of change. In the Java applet, we saw how the concept of partial derivative could be applied geometrically to find the slope of the surface in the x and y direction. In the following two examples, we present partial derivative as rate of change. Specifically, we explore an applications to temperature functions, the example that have a geometry aspect in terms of the physical model itself. And second application to electrical circuit where no geometry is involved. The number one, the temperature on metal plate. The screen capture below show a current website illustrating thermoflow for chemical engineering. Our first application will deal with a similar flat plate where temperature vary with position. The example following, the picture below is taken from the current text in SM221 223 multivariable calculus by James Stewart. We go to the next slide. You can see the color blue, the yellow blue, the yellow color, and the red color. The diagram show. We go to the question how to solve the problem. We can read this. Suppose we have a flat metal plate where the temperature at point x, y varies according to positions. In particular, let the temperature at point x, y be given by Txy equals 60 over 1 plus x squared plus y squared, where T is measured in degree C and x and y in meter. Question: what is the rate of change of temperature with respect to distance at the point 2, 1 in the x direction? And B question is in what the y direction? Let's take A first. What the x direction, right? Look at the slide and we what is the rate of change of temperature with respect to distance at the point 21 in the x direction. What observation and translation can we make here? Rate of change temperature indicate that we will be computing a type of derivative. Since the temperature function is defined on two variables, we will be computing a partial derivative. Since the question asks for the rate of change in the x direction, we will be holding y constant. Thus, our question now becomes, what is delta t over delta x at the point 2, 1? The slide show and ask what is delta t over delta x at the point 2, 1. Since t xy equals 60 over 1 plus x squared plus y squared equals 61 plus x squared y squared power minus 1. Delta t over delta x equal to negative 60 times 2x divided by y divided by 1 plus x squared plus y squared power 2. Delta t and delta t over delta x at point 2, 1, we got the negative 240 divided by 1 plus 4 plus 1 power 2 equal negative 20 over 3. Our final verbal conclusion, the rate of change of temperature in the x direction at 2, 1 is 20 over 3 degrees per meter. Not this mean that the temperature is decreasing. The part B, uh, the rate of the question said the rate of change of temperature in the y direction at 2, 1 is computed in a similar manner. dt we go the next slide. dt over dy negative 60 times 2y divided by 1 plus x squared plus y squared over 2 and delta t or delta t divided by delta y at point 2, 1 equal negative 120 divided by 1 plus 4 plus 2 square equal negative 10 by divide negative 10 per 3. And in electrical, our verbal conclusion is the temperature is decreasing at a rate of 10 per 3 degrees C over m in the y direction. The negative shown the sign for decreasing in 10 over 3. The electrical circuit and we go to the change in current. The following is adapted from an example in a former text from example 22 to 1.223 multiplied by Bradley and Smith. And I equal E over R ampere, E equal to electric and R equal to resistance. The question, at the instant when E 120 and R equal to 15, what is the rate of the change of current with respect to voltage? What is the rate of change of current with respect to resistance? Now we go to the question. Even though no geometry is involved in this number, the rate of change question can be answered with partial derivative. We first note that I is a function of E and R, namely I ER equal ER minus 1. The rate of change of current with respect to voltage, the partial derivative of I with respect to voltage holding the resistance constant equal delta I divided by delta E equal R power minus 1. When E 120 and R 15, we have delta I over delta E equal 15 power minus 1 equal 0.0667. Our verbal conclusion becomes, if the resistance is fixed at 15 ohm, uh, okay, we we look the slide. Our verbal conclusion become, if resistance is fixed at 15 ohm, the current is increasing with respect to voltage at the rate of 0.0667 amperes per volt when the EMF is 120 volts. The part B, last one, what the question asks, what is the rate of change of current with respect to resistance? Using similar observation to part A, we conclude the partial derivative R, the partial derivative of I with respect to resistance holding voltage constant equal delta I divided by delta R equal minus ER power minus 2 when E 120 and R equal 15, we have delta I divided by delta R equal minus 120 times 15 power minus 2 equals negative 0.5333. Our verbal conclusion becomes, if the EMF is fixed at 120 volts, the current is decreasing with respect to resistance at the rate of 0.5333 amperes per ohm when the resistance is 15 ohms. The negative shown a sign for decreasing formation here. Alright, this is for example in chapter 1. Thank you, and that's all.